Hello everyone, my name is Wang Yu, a student from the University of Yamanashi in Japan. Today I will present a toolkit named ExKaldi, which is a Python-based extension tool of the Kaldi automatic speech recognition toolkit. First of all, I will introduce the background of our study. Nowadays, the automatic speech recognition technology has achieved great improvement. Generally speaking, an ASR system firstly extracts the acoustic feature from the speech signal and then uses a decoder to transform this feature to a word sequence. For a typical ASR system, the decoder consists of the GMM-HMM acoustic model and the Ngrams language model. Recently, the deep neural network is used to replace the GMM component to build a better DNN-HMM acoustic model. As we can see from this figure, after introducing the deep learning technology, the error rate of the recognition has been significantly reduced. Deep learning shows its big power in ASR, and in order to develop such systems, tools are necessary. Kaldi is a free and open-source ASR toolkit. It has integrated functions and always keeps track of the latest ASR technologies. So Kaldi is widely used in various studying and developing tasks. But there are some problems with Kaldi. Firstly, as we all know, deep learning technologies are active in some deep learning frameworks, such as TensorFlow and PyTorch. These frameworks adopt Python as their main program language, but Kaldi programs use C++ or shell languages. So it is difficult to apply the neural network models trained with these deep learning frameworks into Kaldi's ASR systems. And the interface tools between Kaldi and deep learning frameworks are demanded. Secondly, Kaldi has a huge command library and specific I/O mechanisms. When dealing with a large task, Kaldi groups these commands with shell script files. These script files are correlated and become black boxes to some extent. So Kaldi is rather difficult to customize in training for Python users who are primarily engaged in deep learning studies. So to address these problems, there are some related work. ESP.NET ASR Toolkit tries to directly use the neural network to transform the feature to word sequence. This approach is called end-to-end model and has relatively simple principle, low memory cost, and fast decoding speed. However, the traditional approach is more robust and still crucial. The second study is the PyKaldi toolkit. The PyKaldi is a relatively comprehensive and exciting code wrapper, but it requires users to write the codes with Kaldi's I/O mechanisms. That increases the difficulties for Python programmers in some degree. Another work is PyTorch Kaldi ASR toolkit. This toolkit provides many network structures for the DNN acoustic model based on the PyTorch framework. But it only focuses on the construction of DNN models. The other parts, such as the feature and label processing and the decoding, completely use the results of Kaldi. This makes it not flexible enough. Therefore, we present our ExKaldi toolkit. It is also developed as a Kaldi wrapper, but different from related work, it has more features than just DNN training, and it simplifies the usage of Kaldi for Python users. And also it provides tools to support the deep learning frameworks. Next, I will do a brief introduction of our toolkit. We use different data structures to hold the active data with Kaldi spiral format and the Python metric, NumPy metric format, respectively. These data are saved in memory or files and can convert to each other easily. Actually, we have designed about 20 data structure classes for different purposes of protecting data or parallel process and so on. Based on these data structures, we have wrapped some standard functions to build the ASR system from the feature extraction to decoding and scoring. The terms appeared in this table are the actual technologies of modeling, but their details are omitted here. In addition, we have expanded some functions. For example, instead of the language model tools provided by Kaldi, we have wrapped two better language model toolkits, SLILM and KELM, to train and evaluate the Ngrams language model directly. And what's more, we have designed some functions to support the deep learning. For example, freely combining different features and labels to customize the multiple tasks, and using our special data iterators to pre-process the data parallelly for training our large-size corpus. This is our Python example code of our toolkit. This script firstly parse the command line option and to get the audio file path, and then extract the acoustic feature from the WIB file, and further process it by applying the feature transformation techniques. Then save the results into file as Kaldi's active format, and also transform it to the Python metric format for deep learning. This is a completely Pythonic program. We have made some effort to try to reduce the difficulties of coding. For example, instead of using the I/O specifiers of Kaldi, we detect the data format and sort it automatically to reduce the coding cost and possible coding errors. This is more friendly for Python user. As mentioned before, Kaldi groups the shell commands with a script file to perform a large task. It is more easy to use, but it is more easy to use that users don't need to understand the internal process. But on the contrary, sometimes the I/O becomes unclear. We also group some functions for convenience, but we clearly tell the user the stuffs used in the process to help user debug and tune parameters. We did some experiments to verify whether our toolkit can build a complete and good performance ASR system. In the next section, I will show you the results. We trained various models from scratch and evaluated their performance. We used the timid data corpus and the trained dataset for training, test dataset for evaluation. The metric of language model is perplexity, and the metric of ASR systems is phone error rate. The smaller both metrics are, the better. Firstly, we have trained various n-grams language models. When training with the same order, we got almost the same score with the Kaldi baseline. And the best result appeared when we use the KNLM backend to train a 6 grams language model. This experiment shows that our ExKaldi toolkit can well support external language model toolkit to help users to train good language models. Then we have trained various GMM-HMM acoustic models stage by stage. As we can see from this table, when use the same condition, we reproduce the Kaldi's result. And at each stage, we also got better results than Kaldi baseline when user better language models we just trained. The next is the result of DNN-HMM acoustic model. We have trained two kinds of neural networks with the TensorFlow framework, the multiple layer perceptron and the popular LSTM models. We compared our results with the Kaldi baseline and the PyTorch Kaldi toolkit. The network structures are almost the same, but our toolkit uses a better FMLR feature and alignment, and the language models generated in our previous training steps. Our toolkit gets the best score. The results reveals that deep learning frameworks can really improve the performance of ASR systems by providing some more advanced techniques and the flexible modeling approaches. And our ExKaldi toolkit can well support these deep learning frameworks to build better DNN-HMM ASR systems. Finally, I will do a brief summary and introduce our future work. In this presentation, we introduce the ExKaldi automatic speech recognition toolkit. It provides tools to it is a Kaldi wrapper and provides tools including acoustic feature extraction, n-grams language model training, GMM-HMM acoustic model training, and decoding and scoring. And it further provides tools to support the deep learning frameworks to build high-performance DNN-HMM ASR systems. Our toolkit is open source now on GitHub, and we hope to add some functions to support the online speech recognition in the future phase. That's all. Thank you for your listening.